Two catchments, the same drainage area, the same annual rainfall, but completely different streamflow behavior. One produces flash floods while the other generates lower peaks but sustains a streamflow for a couple of days after the storm ends. The question is why? The answer is one of the most important concepts in modern hydrology: hydrological signatures. They help us understand runoff generation processes, compare catchments, validate hydrological models, and even predict the streamflow in ungauged basins. In this new series, we will explore hydrological signatures from fundamentals to practical applications. Let's begin. A hydrological signature is a quantitative characteristic of a stream flow that reflects the integrated influence of climate, geology, topography, soils, vegetation, and human activities on the hydrological behavior of a catchment. You can think of a hydrological signature as the fingerprint of a watershed. Every catchment receives rainfall, but not every catchment responds in the same way. These differences are captured through hydrological signatures. Hydrological signatures are important because they simplify the highly complex rainfall-runoff process while preserving the essential hydrological information. By transforming complex streamflow records into informative diagnostic indicators, they help us compare catchments, understand dominant underlying hydrological processes, evaluate hydrological models, and improve predictions in both gauged and ungauged basins. Hydrological signatures can be grouped into several categories, each describing different aspects of watershed behavior. Let's know more about them. First, magnitude-based signatures. They describe the overall amount of runoff generated, including metrics such as runoff coefficient and mean annual runoff. Second, variability signatures. They quantify how much a stream flow fluctuates over time using indicators such as the flashiness index and the coefficient of variation. Third, regime signatures. They describe the long-term characteristics of the flow regime using tools such as the flow duration curve and the base flow index. Fourth, peak flow signatures. They focus on flood behavior by examining peak flow magnitude and flood frequency. Fifth, water balance signatures. They characterize how precipitation is partitioned into runoff, evapotranspiration, and storage. Finally, elasticity signatures. They measure how sensitive a stream flow is to changes in climate forcing, such as variations in precipitation and temperature. Hydrological signatures have become fundamental tools in modern water engineering. They are widely used for hydrological model calibration and validation, helping us evaluate whether a model reproduced the key characteristics of observed streamflow, not just satisfactory performance metrics. They also support prediction in ungauged basins, where relationships between catchment characteristics and hydrological signatures can be used to estimate streamflow behavior in locations without observations. They are also increasingly used to assess climate change impacts, allowing us to quantify how watershed behavior evolves under changing climatic conditions. They are also valuable for detecting the effects of land use change, river regulation, urbanization, and other human interventions on catchment hydrology. Hydrological signatures are much more than a collection of statistical metrics. They provide a concise yet physically meaningful description of how watersheds function. In the upcoming episodes of this new series, we will explore each category of hydrological signature in detail, discussing their physical interpretation, methods of calculation, and practical applications in hydrological modeling. I hope you have enjoyed this video. If so, please stay tuned for the next episode of this series. Thank you for watching. I look forward to seeing you in the next one.